Hi there. It's part three of Physics Week 4 Circular Motion. Left off kind of talking about rotational inertia and how that the farther away from the axis you go, the more rotational inertia you have, which means you don't want to start rotating. You ever see a tightrope walker? They have that big long bar that hangs out over the side. What you're doing is adding mass farther away from your axis of spinning, so it's able to keep you more sturdy. There are lots of other examples that you can easily look up. The angular momentum, just like linear momentum, we talked about in chapter 7, anything that has mass and is moving will have a momentum. So will anything that's moving in a circular motion. The only difference is we call that angular momentum. It goes along with angular speed, which it can be rotational speed. Remember, those two words are interchangeable. How do you find the angular momentum? It's a product, which you're multiplying the rotational inertia and its velocity. Again, it's got to be moving. So you get a couple of, different terms that they show in here, omega, Greek letters, and then your L there. But basically, you just multiply the rotational inertia with its velocity. Didn't give you a whole lot of problems because this is more of a condensed version. Gave you your problems that you're going to have to look at. You'll see are dealing with centripetal acceleration, centripetal force, not with inertia and momentum, but it is able to be figured out. The law of conservation of momentum. Basically, is like any law of conservation. It can't be created or destroyed. So as long as there's no external changes, your angular momentum can't change. So how does that kind of imply? If you've ever seen a figure skater, okay, basically they start with their arms out wide, which is taking your mass away from it. As I start spinning, okay, I have a certain angular momentum, which is my rotational inertia times my angular speed. Well, what happens now as I bring my arms in? I've now reduced the amount of rotational inertia, which then, as long as my angular momentum's the same, has to increase my speed. And that's why you'd see they're moving around. Again, another demonstration I wish we were able to do. I got a little spinny pad that you can sit on. We go down and you hold weights out and you pull them in. You notice you start spinning a little faster. That has to deal with the conservation of angular momentum. The last part of this whole section that I want to focus on is just the fact that you can have simulated gravity. And simulated gravity is that centrifugal force that you would feel. It's not real gravity. Gravity exists between two things. We get into that in the next section. But as you spin something around, the fact that you're wanting to be pushed out, like these ladybugs in here as they're going around, they're wanting to be pushed out. It would seem like it's pushing, as long as you change your direction of what you think is up, would seem like they're being pushed against the floor. And you could do that in space. NASA and scientists have determined you could make a rotational spaceship as it rotates to simulate gravity, because it's that centrifugal force that you would have. It would have to be a really large structure and stuff, and you see it on some of the old and even some of the newer space science fiction type movies where they're in a rotating spaceship. That's to create artificial gravity or simulated gravity. The last part I want to end up with here are just the equations that you would need to be able to do the last two worksheets, which are the circular motion ones. And to find centripetal acceleration. Acceleration can be a change in velocity divided by your distance here, but V then is going to be your tangential speed. So what is its linear speed? How fast are you moving? Now, how many revolutions you're doing per second? And then your radius in meters would be the circular motion that you're making. So a fairly easy equation on that one, which then means to find your centripetal force is fairly easy because we talked about force equal mass times acceleration. So your acceleration, your centripetal acceleration, V squared over R is right here. All we're going to do is multiply the mass in there. And that has to be kilograms, meters, and meters per second. Gets a little more crazy when you start getting to that tangential speed that you want to find, because there's a couple other things you just need to know. And one of those is going to be your circumference, 2 pi r. That's going to tell you that your distance that